Electrical power. When a voltage V is applied across a conductor of resistance R, a current I will flow through it with I equal to V over R. In this process, electrical energy will be converted to heat energy, and electrical power P is defined as the electrical energy consumed per second, that is E over T. Since electrical energy consumed is the product of voltage and charge, therefore the electrical power P equal to VQ over T, which is equal to V times I, because Q over T equal to I. Electrical powers of a conductor of resistance R is equal to P equal to V I. By Ohm's law, we have V equal to I R. Therefore, P equal to VI can be changed to P equal to I R times I, which is I square R. Since I equal to V over R, therefore the power P can also be written in the form of V times V over R, which is equal to V square over R. Therefore, there are three possible formulas for power P. The first one is VI. The second one is I square R. And the last formula is P equal to V square over R. Find the power dissipated by resistors X, Y, and Z in each of the following cases. For case 1, power dissipated by X equal to I square R equal to square of 2 times 5 equal to 20 watt. For case 2, the power dissipated by Y, Py equal to Vi equal to 1 times 0.2 equal to 0.2 watt. For case 3, the power dissipated by Z equal to V square over R, which is equal to square of 3 over 6 equal to 1.5 watt. Case 1. Let's study the behavior when the resistors R1, R2 are connected in series as shown in the diagram, with voltage V1 and V2, currents I1, I2, and the main current is I. First, the ratio I1 over I2 equal to I over I, because in series connection the currents are the same. Therefore, I1 over I2 equal to I over I equal to 1. Second, for the ratio V1 over V2 equal to I1 R1 over I2 R2 equal to R1 over R2, because I1, I2 are the same. Hence, in series connection, the voltage is proportional to the resistance. That means the resistors with greater resistance will have greater voltage. Number 3, the ratio of the power P1 over P2 equal to I1 square R1 over I2 square R2 equal to R1 over R2 since the currents are the same. Again, the power dissipated by the resistor is proportional to its resistance. That means a resistor with greater resistance will have greater power dissipation. Example 1. The current I equal to total EMF over total resistance equal to 24 over 10 plus 20, which is equal to 0.8 ampere. Voltage across X equal to I R X equal to 0.8 times 10, which is equal to 8 volts, while that of Y Vy equal to I Ry equal to 0.8 times 20, which is equal to 16 volts. Notice that the ratio Vx over Vy equal to 8 over 16, which is 1 over 2, equal to the ratio of the resistance Rx over Ry, which you have learned in the last page. And the power consumed by X, Px equal to I square Rx, which is equal to 0.x square times 10, which is equal to 6.4 watts. And power dissipated by Y is Py equal to I square Ry equal to 0.8 square times 20, which is equal to 12.8 watts. Again, notice that the ratio Px over Py will be equal to 6.4 over 12.8 equal to 1 over 2 is equal to the ratio of the resistance Rx over Ry. Again, you have learned this relation in the last page. For case 2, resistors connect in parallel. Consider the circuit with two resistors of resistance R1 and R2 connect in parallel, with currents passing through them I1, I2, and the voltage across them is V1 and V2. The main current is I, and the voltage across the resistors is V. First, for the ratio of their voltage, V1 over V2 equal to V over V. Because they are connected in parallel, they have the same voltage V, which is equal to 1. Second, the ratio of the current I1 over I2 equal to V1 over R1 over V2 over R2, which is equal to R2 over R1, because V1, V2 are the same. Hence, for resistor connect in parallel, the current in the resistors is inversely proportional to the resistance. That means for resistors with greater resistance will have smaller current. Number 3, the ratio of their power P1 over P2 is equal to V1 square over R1 over V2 square over R2, which is equal to R2 over R1, because V1, V2 are the same. Hence, the power dissipated by a resistor is inversely proportional to its resistance, which means that for a resistor of greater resistance will have less power dissipation. Example 2, Part A. Since X and Y are connected in parallel, they have the same voltage. That is, Vx equal to Vy equal to the EMF of the battery, which is equal to 6 volts. For Part B, the current passing through X, Ix, is equal to Vx over Rx, equal to 6 over 10, equal to 0.6 ampere. And the current passing through Y, Iy, equal to Vy over Ry, which is equal to 6 over 20, equal to 0.3 ampere. Notice that the ratio of the current Ix over Iy is equal to 0.6 over 0.3, which is equal to 3, is equal to the ratio of Ry over Rx. You have learned this ratio in the last page. Part C, the power consumed by X, Px, equal to Vx square over Rx, which is equal to square of 6 over 10, equal to 3.6 watt. And the power dissipated by Y equal to Vy square over Ry, which is equal to square of 6 over 20, equal to 1.8 watt. Again, the ratio Px over Py equal to 2 is equal to the ratio of the resistance Ry over Rx. You have learned these relations again in the last page.